welcome to our first session on AI introduction. I am so excited to be here. I am thrilled to have you here. What we're going to be doing starting this morning is we're going to have a shorter session. We're going to give some of the basics that came from NVIDIA, and if we have a little bit of time, I also have some additional material that we can try and share. So first things first, who am I and why should you be listening to me? There isn't a particular reason that you're forced to listen to me other than the fact that I've been doing this for about 39 years. I had my 39th anniversary in AI on March the 3rd. So that goes all the way back to 1986. So I've been doing this for a little while. I've been a consultant, I've been a practitioner, I've been a teacher, I've been a mentor, and I've been exactly where you are as a complete newbie. So I have a lot of sympathy for trying to learn all this stuff and getting into all of the nooks and crannies of artificial intelligence that you may not have heard of before. We're going to work together to make this a collaborative experience and try and make sure everyone gets as much out of it as they possibly can. I am also been doing some of this teaching a little bit at University of Pennsylvania. I've also worked with clients like Coca-Cola, Mercedes-Benz, University of Oxford, Yale University, Aldi, Los Angeles Times, and probably some other organizations you may have heard of. And we're going to go right in and get started. So we're off. So what are the topics, sort of what's on tap for today? Well, the first thing we're going to be doing is just a basic introduction. Then we're going to talk a little bit about what is artificial intelligence, go through some of the history of artificial intelligence. We're going to talk, we're going to skip over this section this morning for NVIDIA Jetson developer kits, because that is actually coming later on. And then we're going to discuss a little bit about deep learning and share some of the details about that. So I hope you're all excited. All right, so what is this course? So first things first, provides a comprehensive overview of artificial intelligence, its use cases, and how it fits into data science and big data ecosystems. Now, one of the things we should all get used to at least a little bit as we go through this process is definitions in this field get a little bit murky. So a lot of people ask, what's the difference between artificial intelligence and data science and machine learning? We've got a slide coming up that's going to talk about that. But the most important thing probably is don't get too worked up about separating out which is which, because as you go through, the primary skills are going to be the same. The primary outcomes are going to be the same. It's going to vary a little bit by audience and who you're talking to. What the original definition that I went from artificial intelligence was the ability of a computer system to perform functions that it wasn't originally programmed to do. In other words, it could learn and gain on its own. That definition has shifted. Now artificial intelligence as a whole is more about the concept of a computer or intelligence system to be able to perform activities and learnings that used to be associated with human intelligence. So in other words, what could we get a machine to do that looks very much like something that a human being who is an expert in the field to do? So we're trying to move closer and closer over time to getting our computers and robotics and cloud systems and everything else to be able to learn and make decisions. That's the basic nub of everything else. A lot of the other details in terms of the definitions we'll go through in a moment, as I mentioned. So we're going to cover core concepts of computational modeling that make up intelligent agents and machines with a focus on embedded and edge computing, and then apply those concepts to, oh my heavens, what a definition this is, isn't it? So let me walk you through what I'm actually trying to say here. With AI, we're trying to figure out how we're going to take these different concepts of being able to make decisions and reflect what used to be only human intelligence and embed them in machines. Specifically with this class, one of the things we're going to be looking at is not how you're going to do all those computations just within the cloud or in your internal architecture, but how you're going to be able to push some of those things out. So if I've got a robot or an automated process or an edge element like a sensor, or let's say that I wanted to control irrigation for my crops and I had an irrigation system that was out there, how much of the decision making can we move out so that each individual, let's say sprinkler system in a field for, let's say I'm trying to raise corn, allow them to be able to take information, make decisions, and move on. So that's very different. So not only is it a more sophisticated way of making decisions, but we're trying to move it so that it's not all controlled in the center. And so that's why they talk about it being edge computing, because it's on the edge of the whole ecosystem. So that's basically what all this is going to be. Now, the second bullet we're actually going to come back and talk about later, which talks about the Jetson Nano, which is an exciting technology, but we don't have that section for you quite ready yet, but there will be at the end. Now, also, just so you know, I hate to be the bearer of bad news, but there are going to be module quizzes and class labs, and we're going to recommend that you do a final project. Now, one of my first reactions whenever I join a course and I see messages like that is sort of, oh no, why are there going to be quizzes? Why does there have to be a final project? Why is there going to be a lab? And the answer is really simple. There's been a lot of research that shows unless you have an individual with hands-on keyboard, actually doing a real world project, going through this information, none of it sticks. And so you go through, that makes sense. Yeah, that makes sense. Got it. Cool. And then 3 weeks later, you're like, what was that? And you have absolutely no idea. It's like the information that you had in class never occurred at all. But when you're actually forced to do the recall for the quizzes, or even better, have hands-on keyboards to be able to process through a project and build that muscle memory to be able to work on these things, it just doesn't stick. It's not helpful. So it isn't meant to make things more difficult or to make things harder. It's to try and set you up for long-term success. All right. So what are learning objectives? Hold on just a second while I get a sip. Learning objectives are to define artificial intelligence. You've already got a head start on that because you just did it on the last slide. List some examples of applications of artificial intelligence, because it's all well and good for us to sit and say, oh, well, it can do this and it can do that, or it has this amazing capability. But unless we're able to actually take those concepts and apply it to what you're doing right now in your current job, what difference does it make? Otherwise, it might be a course on how to do watercolors or oil painting or anything else. Unless we can apply it and actually make an impact on our current role, is not very helpful. Next, describe the different types of hardware implementations for AI computing. So we're going to talk about some of the developments that happened over history. We're going to talk about some of the more recent developments. And in a future class, we're going to talk about how to get you guys set up with your own equipment using Jetson Nano. Next thing we're going to cover is the difference between CPU and GPU processing. If you've already got this down, absolutely fantastic. Great, 2 thumbs up, don't worry about it. If you're looking at CPU and GPU and you're thinking, I'm not really sure what those 2 things are, you're going to be totally familiar with it as we go through. And then you're also going to be able to see practical examples. We're going to take an exercise on a CPU type of chip architecture. We're going to run that command and see what happens. And then we're going to take the same exact thing and we're going to run it against the GPU. And we're going to see what happens. Because your CPU is your central processing unit, your GPU is your graphics processing unit. And one of the huge contributions of NVIDIA to this is the fact that they were able to revolutionize the field by taking technologies that used to be associated only with graphics processors for video games and revolutionize the whole industry to the point where recently they had a current market value of $3 trillion. not billion, trillion dollars. Okay, so we talked some basics about AI. Let's get into a little bit more detail. If you look on the far left of your screen, you're going to see a Venn diagram, which has three components. On the far left-hand side, we're going to talk about human behavior. What do people do? On the far right-hand side, we're going to look at things that only computers can do. So far left, what do humans do? What is their measure of intelligence? Far right, what is it for a system? What's an intelligent behavior that human beings couldn't do? And then there's sort of a central overlap called the Turing test. And we're going to get into a little bit more detail later on. But basically, we're trying to figure out for artificial intelligence, when Alan Turing first worked on this type of research at Bletchley Park during World War II, he was assigned the role of trying to break the German codes in Enigma. Famous movie, Benedict Cumberbatch, The Imitation Game. Keira Knightley, if you haven't seen it, it's a good one to go check out. Talks about all of his research. But his question was, could I set up a test? So if I had a person sitting in one room and they were just typing questions and answers to an unknown respondent in the other room that they couldn't see, could they tell if the person answering the questions was a human being or a computer? Were they able to tell the difference between the two? And what Turing proposed with the Turing test, that's why it's named that, was if you get computer systems to the point where you can't tell the difference if it's a human being or it's a computer system, you have passed the Turing test. You have established a level of AI that is beyond what most people understand. It's going to mimic human intelligence so well that if you apply this Turing test and the system passes it, you have passed the test for artificial intelligence. So that's what that Venn diagram in the upper left-hand corner stands for. Now, if you'll see in the definitions under the scary-looking robot on the right-hand side of the screen, is the emulation of human or biological behavior, which in more common terms is, can we have a system where we can't tell the difference of the behavior? Does it pass the Turing test? Is it a system that shows such ability and alacrity and ability to change assignments that we can't figure out if it was a human or a person? We're also looking at real intelligence that is generated artificially. So what am I talking about here? Well, you know this as generative AI or Gen AI. It's the ability of a system to be able to create something brand new that never existed before on its own. It's creating or it's generating something. So the generating or the creation, hence the generative, hence the Gen AI. Now, this is actually derived from a study of computational agents, forgive me, that act intelligently, and the link is there if you want to pursue that further. So that's basically our starting point. So now we've got one item off the list. What is AI? But how did we get here? Well, I already gave part of the puzzle away in terms of the evolution of AI because we talked about Alan Turing. And we're going to go through a brief timeline, and I actually have some additional elements that I'm going to add to the timeline that are in the slides as we go forward. All right, so the history of AI goes way back and a lot further than you think. So Hobbes was a philosopher and a scientist, as you see, from 1588 to 1679. Thinking was symbolic reasoning, like talking out loud or working out with a pencil and paper. So that was the definition sort of that he was running from for intelligence. And the reason why this is really important is a lot of folks still argue over what artificial intelligence is because it's probably not the best phrase for it in the first place. If you try and get someone to define intelligence, for you. People are very quick to say, you know stuff, understand stuff. Great. Well, if it's just a process of accumulating knowledge, then Wikipedia or the Library of Congress is the smartest element on the surface of the planet. It's the most intelligent because it holds the most knowledge. So we're probably not going to go just on how much knowledge has been collected. We're going to go on to say, all right, well, I think it's more than that, because that's just recall. What are you doing with that? How are you applying it? And that's where things start to get a little murky, because how is intelligence different from wisdom, let's say? Or how is intelligence different from expertise? Or how is intelligence different from other types of elements? And then things start to get murkier. And even today, I just left a position not too long ago where I worked with some of the smartest people I've ever met in my life, who were really experts in their field. And we were just trying to come up with a basic definition of intelligence, because we're talking about artificial intelligence, but no, intelligence itself is. And they had a terrible time coming up with a definition that everyone could agree on. We know it's beyond the accumulation of knowledge. We know it has to have something about the application of that knowledge and some type of way to distill what should be applied and what isn't applied. But does it include ethics? Does it include other elements? It starts to get a little murky. So that's why this sort of pattern over time is so important to understand, because it's still changing today. So Hobbes was trying to just come up with an idea of what thinking or intelligence was. And we're still having that argument, 350 plus years later. All right, so what we've got listed here, we're going to start with, in 1950, Alan Turing asked, can machines think? And that was sort of the generic concept. But you'll be surprised to find out that a lot of the elements of artificial intelligence go back even further than what's listed on this timeline. So, for example, if you were to say, when were neural networks, which are sort of the basis of deep learning that you hear about all the time, what are the concepts for those developed? Well, it goes back probably a lot farther than you think, because if you think of amazing AI scientists, Isaac Newton probably doesn't run to the top of your list. However, he did the basics for discovering calculus and the gradient and gradient descent, which is sort of the curve approximation, where I'm going to take a whole set of data and we're trying to figure out what's a common pattern across those to be able to determine. But that is actually the basis for the most of the AI that we're looking at now. The most common algorithm that is applied for AI today is still logistic and linear regression. Shocker. I know most of you were expecting me to say, oh yeah, neural networks are the most common, used all the time. That's not true. They were developed in the early 1800s, 1807 to be specific. The first artificial computer was developed by Babbage and was actually programmed the first time by Ida Lovelace. Yes, the first computer programmer in the world was a woman. All of this took place before the US Civil War, right? So we're going back a long time. So the first diagram of an artificial neuron for a neural network goes back to 1943. So this is what makes me laugh when people say, oh, we've got to jump on this technology or that technology, or we're going to, magic phrase, fall behind. Maybe, maybe not, but a lot of organizations are losing their shirts because they're not doing AI the right way. And one of the things I've always argued is, yeah, you don't want to fall behind, but maybe we could catch up to the basics of this stuff, which goes back into the 15 and 1600s, before we start worrying about what the competitor down the street just came up with, which may or may not be making any money at all. Maybe we should get into the history and understand the different development. Now, this diagram lists that John McCarthy from Dartmouth College first coined the term AI, or artificial intelligence, in 1956. That's actually not entirely true. Shh, you didn't hear it from me. It's actually 1955. The first artificial intelligence conference was held at Dartmouth College in 1956. Now, only 3 years later, there was an artificial intelligence lab at MIT. So most of us think of AI as something that just came around the corner. It goes back really far. They had an entire institutional lab at MIT in 1959. It goes way back. Now you'll see something on the timeline called an AI winter. Now you're going to hear the term AI winter in a lot of the literature many times. What is an AI winter? In other words, another way of understanding this is you think of winter as something as being cold and maybe desolate and not a lot grows, as opposed to spring or summer. And it's the not growing that is really important when you think about the concept of an AI winter. Because an AI winter essentially means that nothing really happened in the field that was really positive for a long time. And we've actually had 2 of those in the period that's marked here. And it's possible we could hit one again. It's not very likely, but it could be. In other words, we can go backwards, but there's sort of these gaps in history in the timeline where you look at it and like, well, what happened then? Because this stuff goes back to 1600s. Why is there this huge gap between 1959 and 1989? Well, it's not that nothing was developed, but the pace went down really slow, just like I move in wintertime. 1989, NASA developed an auto-class artificial intelligence system, and that was identifying new stars. But I've got a question for you all in terms of somebody type into the chat, what are the organizations that you think pioneered applying artificial intelligence earliest on? Anyone? Type into the chat, what are some of the companies that did the best in this in the very beginning? While I'm waiting for that, many of you probably aren't going to think that Sears Roebuck. Does anyone even remember Sears? It's kind of like Kmart, Walmart a long time ago. Went on for several hundred years. Enormously famous at one point in time. Sears used to do this with their catalog shopping. Banking was also a big pioneer in this. And there was a company that came out to develop a credit score to try and help banks understand who's going to pay back their loans or not. And that was from a pair of guys, one named Fair. Yes, that was actually his name, Fair. And the other one named Isaac, Fair Isaac. So credit scoring was one of the earliest industries to come along with that. Fair Isaac was 1950s. Sears was building predictive models in terms of responses to different offers they would make in the 1940s and 1950s. So those are 2 that you don't hear about so much, but are probably useful to know. In the 1990s, there were the first web search engines, what most of us call just search engines, or so the origins of companies for search were Yahoo, Alta Vista, neither of which are doing so hot. But these are the origins also of what became Google and now Alphabet. And then there was a famous chess match where IBM's Deep Blue beat a world champion chess master named Garry Kasparov. There's a lot of controversy about that, which we may get to in another class, but not today. But these were sort of some of the landmarks. All right, so during this period of the 1990s, computation gets a lot better. There's a lot more data to fool with. And there are also algorithm enhancements. So you've got better hardware, you've got better data, and you've got better software and approaches with the algorithm. That's sort of a trifecta for a win. 2010, the introduction of GPUs, graphical processing units, for which we should applaud NVIDIA, because that was sort of made their launch to fame. Natural language processing and computer vision all came together. And by 2020, we're supposed to have smart homes and self-driving cars, but if you want to be really cool when you're applying, we refer to them as autonomous vehicles as opposed to self-driving cars for some reason. All right, so over this process, there's sort of a timeline that sort of pits those definitions. I promised the slide several times coming on. How does artificial intelligence fit with machine learning, fit with deep learning? And I will tell you that I have surrendered because I did not necessarily agree with this diagram. I have lost that argument. So this is the best way to think of it. AI is the biggest umbrella. So anything you have that is going to be using algorithms or making predictions or that type of thing is now falling under the umbrella of artificial intelligence. Machine learning is actually the process of you have a computer system, you give it a set of data, and you say, this is the outcome I'm looking for. Help me find the pattern in this data. What is the machine going to learn from this data set that I can apply to other things? And the funniest and simplest definition that I really like is actually using stuff you know to predict stuff that you don't know. So let's say you're trying to predict the weather. So you're going to take all this different information about humidity and temperature and wind speed and atmosphere and past storms and how close you are to a body of water and on and on. I'm going to take all this data together. This is stuff I know. I've got readings for all these instruments. I got a big pile of stuff I know. If I look at stuff that happened in the past with that data and say, all right, well, did it rain? Did it snow? What was the outcome of the weather? That was sort of my predictor variables were the temperature and the wind speed and everything else. And my target variable was, is it going to rain or not? Let's say. The machine learns the pattern from old data, stuff we know. Back in time, it looked like this. The outcome was rain or not. Another day, it looked like this. The outcome was rain or not, et cetera, and so forth. You collect all this over time. That's stuff we know. And it identifies a pattern. And that learning is usually referred to in the form of a model. So it's important to understand the difference between a model and an algorithm. The model is sort of the end of the process. The model's going to create prediction. We use an algorithm as a tool to look at the stuff we know that happened in the past, to predict the stuff that we don't know what's going to happen in the future. And how we get from this point to this point is the algorithm. So that's your machine learning piece. So what is deep learning? Well, if you think about machine learning, we just talked about algorithms. There are all kinds of algorithms. There's rule induction, there's neural networks, there's tree-based approaches. There are evolutionary algorithms, such as genetic algorithms, which are all the rage in the 90s. We talked about linear and logistic regression, which come out of the origins of statistics, again, going back to the 1800s, all kinds of different algorithms. Deep learning is a very specific type of algorithm, and it's a subset of neural networks. It's really high-octane neural networks. They're really big. And we don't have to get into too much of the detail on this, but these things are monstrously big. It used to be that when I was first taught back in the age of the dinosaurs about a neural network, the argument was made that if I take an observation of data and I make some predictions, I'm going to put that first prediction in what they call a layer. And then I say, okay, well, what can I learn about the interaction from all these different predictions? And I'm going to create a second layer. And then from that second layer, I'm going to look at all these interactions, still trying to figure out if it's going to rain tomorrow or not. I'm going to create a third layer, and then I'm going to have my outcome. All right. So that type of stuff, those hidden layers, the argument was made that if you have 3 layers or hidden layers in a neural network, you can predict anything. There is no reason to ever have a neural network deeper than 3 layers, because that number of layers is called the depth of the neural network. All right. So when we have that, if they're arguing you only need 3 layers, a lot of people are like, I'm not so sure about that, because I have a model that uses 20 layers, or I've got a model that uses 100 layers, uses 250 layers, or something like that. That's the depth of my model. When it came to later in time, around 2010, 2012, with ImageNet, they said, you know what? That's really silly. I'm going to create a model that has thousands, potentially, of layers to my model. Really gargantuan hunks of stuff. And these gargantuan hunks of stuff, huge models, they were really deep. I mean, if you go from 3 to 50 to 30,000, you're getting really deep. So because of that depth, they call it deep learning. And that sort of started in 2010s, continues today. It's also the basis of most of generative AI. So deep learning became really popular. So how do we put this together? Well, It depends on how you use it. Now, on the left-hand side, we've got an example of a Waymo, which is an autonomous vehicle that's used for taxis. And it's all computer. So you've got cameras, LiDAR, radar, and we've got computers and control electronics. If we've got a human being driving the car on the right-hand side, we've got eyes, we've got our brain, we've got hands, we've got our ears, we listen to the sound. So look at the colors to identify the comparison. So green on each side for Waymo is control electronics. For us, it's the hands to drive the car. The blue is sort of the thinking part. So for an autonomous vehicle, it's the computer. Human being, it's the brain. But how do we get that data into the system? Well, for human being, it's our eyes and ears. For an autonomous vehicle, it's cameras, LiDAR, and radar. So that's sort of how you put all those pieces together and look at parallels across the two. All right, so what do we use this stuff for? I mentioned before, this is really important to get down. Self-driving cars, autonomous vehicles, facial recognition for identification. So as you see now, if you're flying in the US, at least recently, they're starting to take photographs of your face or electronic images of your face as you come through because they're trying to use just facial identification. You can use it for depositing checks. Your Roomba is actually an example of AI network intrusion. So this is cybersecurity, trying to predict who are the good guys from the bad guys. Loan risk models, recommendation engines for shopping and products. All your Netflix recommendations. There was actually a very famous contest called the Netflix Prize many, many years ago. Or we might be predicting, well, the next email I'm going to get a spam or not. So all those different components are involved in applications of AI. Now let's talk about the big bang. So the way our friends at NVIDIA refer to deep learning, or they refer to it as deep neural networks, DNN, deep neural networks. This is deep learning. So this was an evolution in the type of algorithm. But if you're going to have all these really sophisticated, really gigantic models, you need to have better hardware to process them on. And this is where the graphical processing unit, or GPU, became the star of the show. Because computers are really good, in simplest terms, at straight lines and thinking very linearly. So when video games came along, if you remember back in the dark ages when I started video games, they were very clunky and they looked all weird. And they used to have these really rigid edges to anything that showed up on your monitor. Because again, I'm good at straight lines, curves really mess me up. But the way to get around that was to develop a chip that actually handled those curves really well, especially in terms of advanced calculus to calculate that line. It wasn't just changing the processing unit of the algorithm, it was changing the fundamental hardware or architecture. That's a graphical processing unit. So NVIDIA was a huge leader in terms of how to show graphics for video games that involve lines like human faces. So they sat around one day and they're like, wait a minute. If I'm really good at calculating these curves and this advanced calculus, my chip works so much better than that. All this deep learning stuff, the calculus is actually pretty similar. So I'm going to use gradient descent or some other application. Well, if my chips are really great at doing this for putting an image on the screen, I'll bet they're pretty good at calculating those same things when they're involved in predicting a model or a neural network. So they thought, you know what? I think we should expand way beyond doing chips that have a special architecture just for video games. We're going to apply it to deep learning and artificial intelligence because we can make them bigger, faster, cheaper. And that's exactly what they did. And that's what most people think about NVIDIA today is their chips for AI. And the chips today are obviously much more sophisticated and have much more additional add-ons and optimizations than just calculating the gradients. But back in the day, that was sort of the easiest way to understand it. So we've got our DNNs, which are our algorithms. We've got our GPU as our hardware, and then the evolution of big data. Meaning that if you've got much more data available, because there's an explosion of the growth of the web, can we take that data from the web and apply it to this? So if I've got better algorithms, I've got better hardware, and I've got better data. Remember we said before, that's a pretty good trifecta for doing really well. All right. Now, we're going to go to what we're going to talk about for this course involves a lot of deep learning and GPUs. I totally warned you ahead of time that we're going to skip this part in terms of the Jetson Nano, and we're going to come back to that in a future class to discuss that. All right, so how do we actually get this stuff to work? All right, great, I got an algorithm, I got an algorithm. Scott, that's wonderful. What I'm actually going to use in terms of programming these GPUs we just talked about. And I'm not going to read all these to you because you can read perfectly well, but if you look through this, you get an idea of how to convert existing programming languages to this new frontier of GPUs or graphical processing units. And there's the list. Now you're going to notice CUDA or CUDA, as it's referred to, as an application for a lot of these things. And CUDA is one of the things we're going to be covering later in the class. So be aware of that. For NVIDIA, we're going to have the process of a whole developer toolkit, which is the CUDA toolkit, which we'll be talking about as we go further through the class. And then we've got a bunch of resources here for getting more on deep learning. I wouldn't worry about memorizing all this today or going out to next week. We're going to take it nice and slow and make sure everybody's up to speed with this. It's going to be good. But if you want additional resources on how deep learning works with neural networks, we've got resources for you there as well. Now, there are also things that are called GPU frameworks. So a framework is a more sophisticated, and just like a framework for a building, or if you had a framework to sort of put scaffolding up. It's a sophisticated system for holding this type of code and this processor. And there are a bunch of them. Caffe is one, MXNet, TensorFlow, PyTorch are the most popular. TensorFlow is amazing, but makes my head hurt because I found it really hard to learn. So I'll just put that out there. But it has amazing capabilities. If you can master TensorFlow, you're in good shape to do a lot of different stuff. Now, Python has become the most popular language for doing machine learning because it was open source. Now, back in the day, it used to be if I wanted to build a predictive model, I had to go out and buy some pretty expensive software. And a lot of that software, such as the old version of SAS, SAS, not SASS, not software as a service, but SAS, the company, statistical analysis software, used to be pretty pricey. But everyone used it. But it was like, I don't know, I'll use your numbers, like $2,500 per person in your organization to use this. So if I got $2,500 but I got 1,000 employees, we start talking about some real money per year to be able to use this. Python was already a coding language that was around. And a bunch of organizations were like, well, why couldn't we use a free or open source language to do some of this stuff instead of paying all that much money? So in the era of open source, doing these things for artificial intelligence, machine learning, creating applications for that would have been really helpful. So people are like, well, this Python thing seems to be easier than a lot of other ones to use, and it seems to be really flexible. Maybe we'll just create libraries of routines from Python to make this stuff work. And so that's why Python became sort of the lingua franca across there. So here's a whole list of languages, frameworks, libraries that apply Python specifically to the type of projects we're going to be working on. And that is the end of our presentation this morning. So I'm going to come back over here and I'm going to say, anyone has any questions, please type them into the chat. Any questions? Anything I can help answer? Anything I can help address? Not seeing anything? All right, well, then we will continue our discussion next week. Look forward to seeing you then. Thanks, everybody.